How's it going, everybody? Welcome back for another video here looking at Unit 2 of Sensation and Perception. This video is going to focus a little bit on the basic idea of sensation, some different types of disorders that could happen, and as well as the overall sensation of vision. Without further ado, let's get started. So in our last video, we talked about many of these terms: sensation, absolute threshold, and just noticeable difference. But we also have another idea called sensory adaptation. This is the idea that if we're constantly exposed to some type of sensation, like a sound or smell, we get used to it and we kind of ignore it. So things like living next to a railroad. When you first move next to a railroad, you might notice every single train that goes by. But if you've lived there for a while, your brain just kind of blocks out that sound. You get used to it and accustomed. This idea of Weber's law below is another term that for many of us can become kind of confusing and hard to explain, but let's kind of dissect it together right now. This is the idea that instead of a constant amount that should increase for us to notice when it comes to a change in weight or some type of sensation, it's a percentage of increase or change being what matters. What that kind of means is, for example, if you have 10 pounds of weight in your hand and we add 1 pound to that, you might notice a pretty decent difference. The reason why is because that 1 pound compared to the 10 in your hand is about a 10% increase of that overall kind of basic weight. That's a 10% increase, so you'll notice that change in weight. Whereas if you're holding 1,000 pounds, or let's just say 100 pounds for right now, and we add 1 pound to that 100 pounds, that's only 1% of a weight change. And for that, your body might not notice or be as sensitive of that change to detect it. So basically what Weber's law is telling us is that we will notice a percent change way more than an overall number change in something. 1% is a lot different than 10%. So that is Weber's law. Easy way to remember that is the W for weight. Many questions kind of lean on that idea of weight. So going back to these two topics that we talked about before, absolute threshold and just noticeable difference, we have two visuals here to kind of help explain these terms for you. Absolute threshold means that it's the bare minimum for you to detect something with your senses about 50% of the time. So anything under this threshold are sounds or smells or brightness that we cannot detect with our senses. Now, when we're younger or in our prime, our threshold is lower, which means we need less and less of sensory information to be able to detect it. We can hear very well, we can smell very well, taste, touch, see, etc. But when we get older, our threshold goes higher, meaning we need more and more volume or more and more smell to be able to detect it with our senses. So the idea, just kind of to wrap it up one last time, is that we have to hit a threshold to be able to detect things with our senses. Now, just noticeable difference is the idea that there's a bare minimum we need to be able to detect changes in some sensory information. Let's say volume. Let's say our base volume is this green over here. If we crank up the dial 2 for these yellow, our senses won't be able to notice that difference. Even though that we can see that there is an actual change of the volume, our brain isn't as sensitive enough to notice that minute small change. Once we get one more into that red is when our brain goes, oh, this volume seems louder, this song seems louder on the radio. So basically we have to hit a certain amount of change for us to actually notice that something did change. Now, this idea of sensory interaction just means that our senses work together. So for example, our sensation of smell also works with our sensation of taste. This helps us create the idea of flavor. So the reason our food has certain flavors and things of such is because our senses are kind of working the same job with each other to give us that experience. That's why, for example, when we're sick, we might not be able to taste food as well. Even though our taste buds are fine, they work hand in hand with each other. And if one system is out of whack, the other system is also probably going to have some issues as well. Another main topic you need to know for the AP exam is that taste and smell is based on overall past experiences, as well as our cultural and societal expectations. What this means is we might, for example, have an experience with an apple, and maybe it was a great time, but this apple was very sour and nasty. That one experience can make you dislike the taste of apples. That's a personal past experience that influences your overall idea of taste. Now, on the flip side, for cultural expectations, certain cultures are exposed to certain types of foods or different ingredients more than others, which means that we might tend to lean more towards our cultural foods, for example, compared to other cultures' foods and spices. This is just because in our culture we're expected to like a certain style of food, and it might be something common at parties or holidays or celebrations. And this kind of ingrains in us this idea of what is good food and what is bad food. Now, a rare phenomenon we want to talk about is synesthesia. This is a condition where our senses sometimes cross and kind of lead into each other. What this means is they might kind of go into this blended form of sensation. We might see color when we listen to music, or when we hear words, we might have a taste in our mouth. Basically, two senses are firing together, even though we're only taking information from one sense. If we're taking in something visually, we might hear something that kind of connects with what we saw visually. Now, moving on to the actual sensation of vision, here's an idea of how the process works. Light waves hit our eye, and they do something called transduction. Transduction is when we take energy, for example, like a light wave, and turn it into a chemical signal. Our brain speaks one language, and it's chemicals. It doesn't understand light waves or sound waves or vibrations. It needs a chemical to be able to understand and perceive the world around us. And each different sensation has a way to do transduction. For vision, we're going to talk about the retina, which is the part of the eye that does that. And we're going to begin that right now talking about the process. So light waves are going to hit our eye, if you look at the kind of the top right, and hit our pupil. And it hits something called the lens. It kind of looks like a contact over here. And what it does is with that light energy, that light wave, it refracts it out in different directions, hitting the back of the eyeball. Now, in the back of the eyeball is something called the retina. Easy way to remember the retina is the R for the rear is in the back of the eye. This membrane has two types of cells in it, bipolar and ganglion cells. These specific two cells take in this light wave and do transduction. They turn it into a chemical to be sent through the optic nerve to the brain to be processed. So you also have to remember the optic nerve is this nerve kind of here and back that sends that signal out of the eye to the brain. Now, in addition to the bipolar ganglion cells that are turning waves into chemicals, we do have two other types of cells in the retina as well. We have cones, which help us see color. Think of C for color. And rods that help us with things like shape, movement, and shading, specifically black, white, and gray vision. Now, if you look at this image up here, when the light waves hit our eye, there's one little spot here called the optic nerve. Now, that optic nerve doesn't have any cones or any rods on it. It's kind of like a dead spot in the back of our eye. So if any light hits that, this is what causes a blind spot. A blind spot is if any type of light wave hits that optic nerve area and there's no cones to perceive it, which means we have no vision in that small spot in our blind spot. Now, we don't see this giant kind of smudge in our vision of where we can't see. Our brain just fills in the gap, and that's called the incomplete retinal image. Basically, despite having a blind spot, we kind of fill in the middle of our space with any missing detail to make sure we don't have this blotchy kind of void in our vision. This kind of shows us again how the eye process works. Light waves hit our eye, refracting off that lens and hitting that retina. Now, inside that retina are our cones and rods, which help us perceive shading and color, but also these ganglion and bipolar cells. These ganglion and bipolar cells turn this energy into a chemical that is shot out through this optic nerve that we can see here. So it goes in, hits the lens, hits the retina, out the optic nerve. All right, a few other issues when it comes to vision. One of them, before we get into the actual issues, is how our eye adjusts to things like looking far away or close, and that's called accommodations. Accommodations means that our lens, that kind of like contact part of the eye that looks like a almond, will change its shape whether we're looking far or close. If we're looking far away, for example, it looks to be this kind of smushed, skinny lens. So if you look at this image here, you can kind of see it at the top right. When we're looking far, it has to kind of squeeze and make itself very skinny to help us focus in a long distance. Then we look at stuff that's close by, our lens gets very wide, almost like a ball, to kind of collect as much data as possible. Now, going into those issues that we were talking about, nearsightedness is kind of this condition where we have difficulty seeing distant objects. We have difficulty accommodating to see far away. Where farsightedness is the opposite. This means we have issues with seeing things that are close up to us. Our eyes can't accommodate into that big wide ball to help us with perceiving that sensory information. Easy way to remember this is nearsightedness. That near sight means you can see close, but issues with seeing far. Far sight means I can see far, but I can't see close. And then there's two types of color vision deficiencies we want to talk about. One is dichromatism. This is the idea that we're missing one of our three cones in the eye, which means we can see most colors, but we have issues with reds and greens. These two colors kind of cause us difficulties, and we might get them mixed up pretty often. Now, monochromatism is a color vision deficiency where we cannot see any color. Everything is monochromatic. It is black, gray, and white shades. There's no true color anymore in our vision. This shows us the example of accommodation. When we're looking far away, we have this very smushed and skinny kind of wide lens. When we're looking close by, our lens gets very thick like a ball to take in as much information as possible. Now we have examples of nearsightedness and farsightedness over here. An example of monochromatism, which means over here on the right, we have no color, for example, those colors of paints. Now we're going to go to our final kind of aspect for today, and that's going to be vision theories. We have two ways that we think that vision works. The first one is trichromatic theory, which means that we see the world around us in three colors: red, green, and blue. Everything that we see and perceive is a mixture of these three color hues that work together to see things like magenta or yellow, etc. Now this helps us understand how we detect color with our cones. But the other theory we're going to talk about is the opponent processing theory. This is how we process and perceive color. This is the idea that we see color in pairs of opposites. When one color is stimulated, the other one is blocked and turned off. And then if they get fatigued when we look away, we see after images and opposite colors sometimes, which means that, for example, if we're staring at something that's bright red and then we look away, we might see an afterglow or an after image of a green color. So the opponent kind of opposite colors are as follows. We have red that switches back and forth with green, yellow and blue switching back and forth, and black and whites. This just kind of explains why we have after images and things of such. Now that's it for this entire kind of video today, going over vision and some of the basics of sensation. Hopefully this helped you, and hopefully this helps you prepare for those exams. Have a good one.